In this video, we're going to go over the first unit from General Chemistry of the Ancient Brain CP and BB content course, which covers the high-yield CP and BB information. To check out that course, there is a link in the description below. This unit and a few others are available for free, and you can subscribe for access to all of the others. Here's the list of topics that will be covered in the video, and we'll start with Unit 1.1, Atomic Number and Mass. First, let's look at how elements from the periodic table are represented. Here we have the letter that represents the element that you're working with. So for example, if you have something like carbon, that letter will be C. All elements can have three numbers, the first one being the atomic number, and that represents the number of protons that are in the nucleus of that atom. The second one is the atomic mass, and that is the number of protons plus the number of neutrons that are in the nucleus of that atom. The third one is the charge, and we find the charge by subtracting the number of electrons from the number of protons. You won't always see the atomic mass and the atomic number written in those exact spots, but you can always tell which one is which because the atomic mass will always be the larger number because that's the protons plus the neutrons, where the atomic number is just a number of protons. One really important thing about the atomic number is that that's what determines the identity of that element. So whether or not an element is carbon or nitrogen depends on whether that element has 6 protons or 7 protons. It has nothing to do with the number of electrons it has or the number of neutrons that it has. I'm going to quickly draw an example atom that has an atomic number of 6 and an atomic mass of 13. And the charge is neutral. I'll use red to represent the protons, so I'll draw 6 protons. I'll use blue to represent the neutrons, and here I have to draw 7 neutrons because we need our protons plus the neutrons to equal 13. The charge is 0, so that means we have the same number of electrons as protons, and as you probably already know, those electrons are not part of the nucleus. They rotate around the nucleus. A couple of final notes here. The two things in the nucleus, the protons and the neutrons, have a mass of 1 AMU. An AMU is an atomic mass unit, and it's just a really, really small unit of mass used to show how much a proton and a neutron weigh. Electrons, on the other hand, have a negligible mass, and that's why they are not considered whenever we calculate the atomic mass of an atom. Lastly, anytime an element has a charge, you need to adjust the number of electrons. Do not adjust the number of protons, because if you change the number of protons, you change the identity of that element. Now we'll talk about isotopes, and isotopes are two atoms that have the same number of protons, but a different number of neutrons. And since they have the same number of protons, they are the same element. So both of these are carbons, despite having a different number of neutrons and different atomic masses. A topic that's closely related to isotopes is atomic weight. Atomic weight is the number that you would get if you took all of the atoms of a particular element and then took the average atomic mass of all of those atoms. The way that we can calculate that number is to take the atomic mass of each isotope, multiply it by the percent abundance of that isotope, and then do that for every isotope of that particular element, and then add those values together. The percent abundance of an isotope tells you what percent of all of the atoms of that particular element are that isotope. So for example, carbon-12 is one isotope of carbon. It has a percent abundance of 98.9%, which means out of all carbon atoms, 98.9% of them are carbon-12. You'll also notice that atomic mass is always a whole number since it's just counting the numbers of protons and neutrons of one particular atom. But the atomic weight will always have some decimal because we're taking the average of all of those atomic masses, so it doesn't come out to be a clean whole number. Now let's go through example 1.1, and here we are trying to find the atomic weight of carbon, which has two main isotopes. One has 6 neutrons and one has 7 neutrons. So for the first isotope, we're dealing with an atomic mass of 12. For the second isotope, we're dealing with an atomic mass of 13. The percent abundance of the first one is 98.9, and the percent abundance of the second one is 1.1. Now we need to plug those numbers into equation 1.2, and that gives us 12 times 98.9%, which we need to write as decimal form, so 0.989, plus 13 times 1.1%, and in decimal form, that is 0.011. And that added together will get us the atomic weight. Anytime you're practicing your math from here on out, make sure you're doing it without a calculator, since that's how you're going to have to do it on the test. You'll have to develop some creative ways to go about solving some problems, and here's a good example of one, because 12 times 0.989 is something I can't do in my head, so now I have to think about how can I go about solving this without a calculator. And since we don't have a calculator, we can do some rounding, and we can turn that into 12 times 0.99. I'm going to solve 12 times 0.99 off to the side here. 12 times 0.99 is not something that I can do in my head, but I know it's the same thing as 99% of 12, which is the same thing as 12 minus 1% of 12. So what you see in parentheses is the same thing as 1% of 12. 1% of 12 is something that I can solve a lot easier because all I do is move the decimal point 2 places to the left on 12. So then I end up with 12 minus 0.12. 12 minus 0.12 is 11.88. And I will plug that back into right here. So we have 11.88 plus whatever 13 times 0.011 comes out to be. As you solve 13 times 0.011, remember that you can do some rounding and we can turn that into 13 times 0.01. And that's really similar to the problem that we just did. All we need to do is move the decimal point 2 places to the left on 13, which gives us 0.13. Now we have a simple addition problem of 11.88 plus 0.13 to give us 12.01 for the atomic weight of carbon. The last topic that we'll cover is the strong nuclear force. Protons and neutrons exert an attractive force over other protons and neutrons whenever they're in extremely close proximity to one another. And that force is the strong nuclear force. I have represented that strong nuclear force with that purple line here. So if these two protons get close enough that the purple lines overlap, they will be attracted to one another and stick together. This is really important because protons are both charged particles, and since they're the same charge, they will repel one another. And without the strong nuclear force, the nucleus of an atom couldn't stay together because of that repelling force that the protons have on one another. I've drawn the orange circles around each of those protons to show that repelling force that they exert on each other. In reality, that force doesn't have a definitive boundary like that. It just gradually gets weaker, but drawing it with that definitive boundary just helps with this explanation. What it helps us see is that the strong nuclear force only exists super close to the proton. So if the purple circles are not overlapping, the protons will only repel each other, and they can't stick together to form a nucleus. However, if we can get the purple circles to overlap, the strong nuclear force will overcome that repulsion and make those protons stick together. And that's because the strong nuclear force is much stronger than the electrostatic repulsion. Understanding the balance between the strong nuclear force and the electrostatic repulsion between the protons helps us understand nuclear fusion and nuclear fission. What I'm about to explain is only applicable to much larger nuclei than what I've drawn here, but this drawing is good enough to help me explain the concept. Just make sure you understand that it would require a lot larger nuclei for this to be applicable. We are going to focus on the proton here and the proton here. So since these two protons are further apart, they are repelling each other due to that electrostatic repulsion, but they are not attracted to each other because they're too far away for the strong nuclear force to take action. What this means is that this proton is getting pushed away by that proton and vice versa. And this repulsion that's happening within this nucleus makes it more unstable. And the larger a nucleus gets, the more unstable it becomes because of this. So for nuclear fission, we want to use larger nuclei to split, and for nuclear fusion, we want to combine smaller nuclei. That's it for Unit 1 of General Chemistry, and you can access the PDF that we just went over via the link in the description below. If you liked this video, subscribe to the channel for more MCAT related content.